All right, welcome back. Problem 53, page 435. This is homework set 29, and it is a sister to problem 27 on page 428. This problem is actually taken out of the chapter summary. That's why the pages are different. And it's another AC, or alternating current circuit application. Pretty simple. We're given an expression for the current, the time-dependent current in an AC circuit, and we're asked to find the period, the amplitude, the phase shift, and then graph the thing. And I think they want you to do two periods. Yeah. So let's we can knock these off pretty quickly. First of all, what's the period? I think you remember that the period, the time for one cycle, is 2 pi over omega. And look, if we look up here, in this case, omega is equal to 30 pi. So if we just insert the omega in here, we'll get, for our case here, it's 2 pi all over 30 pi. The pi's cancel, and you get 1/15 seconds, 1/15 of a second. So let's put that answer right here. So every 1/15 of a second, this circuit runs through one cycle. What's the amplitude? You really just need to look up there, right? The sine, the naked sine has it has an amplitude of 1, meaning it goes between -1 and 1, minimum -1, maximum of 1. If you multiply that sine by 220, remember the idea of transforming functions. This is a stretch. 220 is bigger than 1, so we'll stretch the sine vertically so that its maximum is 220 and its minimum is -220. And in these applications, this amplitude will have units, and in this case, the current is measured in amperes. So problem C is the one that we want to just take a heartbeat and spend a little time on, because it's very easy to look right up here and say, well, you want the phase shift, there's the phase shift, and you would be wrong if you did so. In this expression, in this manner, this is actually called the phase angle. It is an angle, after all, right? Sine is operating on angles here. This is an angle. Omega times t is an angle, because this is a radians per second. This is a second, so this quantity has units of radians, as does this phase angle. In fact, you know, we're studying problems of waveforms of the form a constant times cosine or sine omega t plus phi, and that quantity is called phase angle, phi for phase angle. If you want to find the phase shift, it's necessary to rewrite this argument by pulling the omega out in this manner. And the reason, and this is called the phase shift. And again, appealing to what you know about transforming graphs, if we replace t with t plus phi omega, you know that what that does is it literally shifts in this case, shifts the graph backwards by this amount. Backwards meaning to the left, right? So here's the phase shift. In our case, phi over omega is equal to, where the heck is phi? Pi over 6, and what's omega? 30 all over pi. So good luck to us trying to figure that out. That's equal to pi over 6 times 1 over 30 times pi. It's equal to 180th of a second. Okay? 180th of a second, which is going to make the graph kind of interesting to draw, because on this scale, 1/80th of a second is probably smaller than my thickness of the ink I'm using here. So here's time. Here is I of t right here. Here is one period, 1/15th of a second. Here is the end of the second period, which would be 2/15ths of a second. And so the sine is just starting from 0, as it always does. I'm going to make a caveat to that in just a second. runs up, runs down, runs to 0, runs up, runs down, runs to 0. That's effectively what it looks like, and apologies for that. I evidently had too much coffee this morning. But remember, that's the sign. What instead we're supposed to draw here is the sign that is phase shifted by this amount. Now, well, the difficulty is, as I said, I'll draw it like this. This blue line is shifted to the left of the magenta line by, I'm just going to cheat and say that is 1/180th of a shift. So that point right there is not 0, 0. It's minus 180, 0. That point right there. And so there you have it. Onward.